Okay, so as I had mentioned in the previous video, we're going to be talking about maximum average power transfer. So that's what we're going to be looking at here. And there's several ways to look at this here. If we recall here, when we're dealing with just resistors, we knew that max power transfer occurred when the load resistance was equal to the Thevenin, or sometimes we refer to that just as the equivalent resistance of the circuit. Now, if we're talking about just our steady state, we now have resistors, inductors, and capacitors, and we do impedance. Z. So what we're asked to find then, of course, is, well, we want to know what load should I attach for maximum average power transfer. Now, it's important here, I'm saying maximum average power transfer is not necessarily maximum power transfer, because when we talk about complex power, remember we've got lots of different things here. We've got complex power, which is volt amps, we've got reactive power, which is volt amp reactive, and we've got average power, which is just our P, which is in watts. And so we're really looking for maximum average power transfer. And you might say, well, why would we want maximum average power transfer? And well, the reason being, of course, is that, well, the average power again is what turns a crank. So your guess might be that, based off of what we did for resistors, you might guess that, well, I'm just going to set my load impedance to my Thevenin impedance. And you're close, but not 100% correct. You actually want to do the conjugate of the Thevenin impedance. And the reason behind that is you're really wanting to kind of cancel out that reactive component. So we're going to look at a very simple problem here. This isn't a proof. Most textbooks have this as a proof in there as why this gives you maximum average power transfer. But I like to just go through a simple example to kind of illustrate it here. So we're going to go through this example here, where we're going to just have, well, let's just even do 10 volt, and we'll do RMS just for simplicity, at an angle of 0 degrees. And we'll have a 20 ohm resistor, a minus Gen 10 ohm capacitor, and then, we'll have my load attached here. So we're going to say what load for maximum average power transfer. So what load should I put on there for maximum average power transfer? And this is really easy. This is a very basic circuit. In fact, this would be written in a Z Thevenin, or not a Z Thevenin, a Thevenin equivalent here. So we can just see by inspection here that my Z Thevenin is simply 20 minus J10 ohms. So that means my load I would want would be 20 plus J10 ohms. And so then we can clearly see here that this would be just simply a resistor and an inductor. 20 ohm resistor and a J10 ohm inductor. So I'll just go ahead and redraw that circuit real quickly. With the load in now. And so this was 10, an angle of 0 degrees, and again this was volt RMS. And this was 20 ohm minus gen 10 ohm, 20 ohm, J10 ohm. Now, what's actually, I mean, you could compute the power in a lot of different ways here, but if you think about this, if I have a circuit that's like this, actually computing my current here is going to be very easy to do because it's a series circuit now. And not only is it a series circuit, but you would have 10 volts is equal to 20I minus gen J10I plus 20I plus J10I. And what we want to see here is, of course, these J components just cancel out here. In essence, we're canceling out the reactive portion of it, and we get that 10 is just simply equal to 40I. And so, doing my arithmetic correctly, we get I is equal to 0.25 amps. Okay, so then let's go ahead and figure out what the average power here would be through this. So let's first just go ahead and compute the complex power through the load. So I'll do S times the load, which remember is the magnitude of I effective squared times my impedance, which in this case is fairly easy because my I is just completely real and it's already ineffective. So it's 0.25 squared times 20 plus J10. And just using my calculator so I don't make any silly mistakes, this would be 1.25 and plus J 0.625 volt amp. So I mean that's what gets applied to the load here. But as far as my average power here, P is equal to 1.25 watts. So that's my maximum average power transfer. Okay, so to kind of, this again is not a proof, but to kind of illustrate why, or to show that this is definitely giving us kind of a maximum average power transfer, let's now just assume we attached a load of 20 plus J5. So if I do 20 plus J5, clearly we do not have that my load does not equal my Thevenin impedance conjugate. Okay, so then, you know, the analysis is still going to be the same here, except I'm going to have now 10 is equal to 20I minus J10I plus 20I plus J5I, which of course is going to give you 10 is equal to 40 minus J5 times I. So if I do that, we get, and I'm going to carry out a couple decimal points here, we get that I is equal to 0.246154 plus J 0.030769 amps. Now I'm going to go ahead and convert that to polar. So if I convert that to polar, if I can remember how to use my calculator here, we get 0.248 at an angle of 7.12 degrees. Alright, and this would be, of course, amps. And so this, of course, here is my magnitude of I effective. And so I would want to square that and multiply it by my load here. So basically, if I want to know what my complex power is, S would be 0.248069 squared times my load, which is 20 plus J5. So I do that 0.248069 squared times 20 plus, oops, forgot to type it in correctly, plus 5J. You get that S is 1.231 plus J.3077 volt amp. And we can see here now we don't have we don't have as much average power, because my average power here is 1.231 watts. And if I scroll back up, we got 1.25 watts when we had done the proper load. And we can kind of see what's going on here. What's going on here? Well, there's a couple things. One is that I don't have purely real current here. So I've got some imaginary component of current here. I'm sorry, I don't have purely real power, so I have some imaginary component of my power. But the same thing here, my current's not completely real. But then really, if you think about here, when you're doing the division, you would be doing 10 divided by 40 in the first case. But here, when you do this division, you're dividing by a larger number. And how do I know it's a larger number? Well, if you think about 40, if you convert it to polar, 40 minus J5 goes to, so let me just do that, 40 minus 5i, math to polar. You get that this is 40.31 at an angle of negative 7.12 degrees. And so we shouldn't be so surprised here, because if I just did everything in polar form, I would have I is equal to 10 at an angle of 0 degrees volts divided by 40.31 at an angle of negative 7.12 degrees, and that would be in ohms. And then, of course, well, we can see that's why we get the positive 7.12 degrees. But then notice, what am I dividing by? I'm dividing by a slightly bigger number here. In the first problem, what was I dividing by? I was dividing by 40 here. When I did it the first time, I was dividing by 40. Now I'm dividing by 40.31. So I'm dividing by a slightly larger number. Now, of course, it can be more extreme depending on the size of the imaginary impedance portions, as far as not getting as much average power transfer. So the key thing here, just to end, and we'll star this here, is that for max average power transfer, you need to set the load impedance to the conjugate of the Thevenin impedance.